So we have some question about the in the PPT we saw some of the mathematical calculation.
Okay.
So I think you can support us to explain the mathematical calculation. We are not very familiar
Okay.
about this.
Okay. Thank you all for joining this class. Yeah. We will start our class today. Is the presentation. Their presenter will be Aloha,
Yes.
Andrew, and Farah. Yeah. Okay. There are 3 members in this group, and they will talk about power flow. Yeah, I think this content you have learned this in your undergraduate course. So I think it's a lot of very difficult. But maybe you have learned this 7 years ago. So just pay attention, and I think you can easily understand this. Okay. If you have any problem after the presentation given by the presenter, I can also discuss with you. Okay.
Okay.
So can you start your presentation? Aloha.
Yes. I can start. Thank you, Larshi.
Okay.
Good evening, everyone and every my friends. Because of we are far away from us a long time we don't see because of due to COVID-19. So I'm really happy to see all of us too in this class. So in this course, especially we focus on transmission system effect as a power flow. Our course name is the power system operation and control. Actually, in this course, we will try to understand and try to study to how to control the transmission, power flow, and power system. So let's discuss. Today's in the PPT we have 25 slide. So we are 3 presenter, and every presenter we can cover 8 pages. 8 pages. So let's start to beginning the power flow. Actually, at first we need to understand what is the power flow, and the power flow is the most important and essential approach to investigate problem in power system operating and planning. That means this is the one kind of investigation to this is the one kind of investigation to find out the problem in our transmission line or transmission system and reduce the loss. Okay, let's discuss the overview. What we discuss in this in our presentation. We can here we see the network incremental power losses causes basis. That means the impact of loss in the optimal economic scheduling of the generation. That means when we transfer the transmission system, when the transfer the electricity or electric power, there have a lot of losses, and this loss make us a lot of high cost. So if we find out the problem and if we solve the problem, then our transmission cost is lower. This is economically we will be benefited. The total real power loss increase the total generation demand. I already tell that the increase the total generation demand. That means if the loss is very high, our generation demand is also very high. The power flow forms the basis for the development of losses factors of predicting the real power loss. This is one part. Another part is that the generation schedule may may need to be adjusted. That means the generation schedule, when the generator always generating the power, we need to adjust the shifting generation to reduce follow on transmission circuits. Otherwise, they would become overloaded. That means we should need to control it, and we should need to the shifting type. Shifting is properly shifting or not. So we need to consider about this. Otherwise, if one single generator always running, that time it will be overloaded. And when it will be overloaded, it will make a accident or make a any kind of how to say the violation. Difficult to include the last effect into optimum dispatching. This is another part. Another part is that the power flow must be solved to check for violation. That means with the power flow always we need to check for the violation if any kind of accident or any kind of violation not. So this is the overview of this our today's presentation. Okay, the power flow problems. The power flow is the name is given a network solution that shows as current, voltage, and active and reactive power flows at every bus within the system. That means here is very clearly right. Actually, what is the power flow? That the power flow is this. It shows current, voltage, active and reactive power flow is every bus within the system. That means if we have one system, we can in the power flow can shows in the system every single point, every single bus point, it show current, voltage, active and reactive powers. The assumptions the balanced system, positive sequence solution only. The simple generation and load method. Here is the non-linear problem. The related active and reactive power consumption to generation with voltage magnitude. This non-linear problems we can generator with the voltage magnitude. And uses design, procedure, system planning, study unique operation problem, provide accurate calculation to loss penalty factors. It means that we need to design the perfect procedures and study unique operation problems and provide the accurate calculation. We need to calculate. We need to at first identify the current, voltage, and active reactive power, and accurate calculation of loss penalty factors. The power flow problems, we can see the power flow problem consists of a given transmission network. The given transmission networks, it means that the transformer, generator, and loads. The transformer, generator, and loads. The transformer is represented by a series. The line are represented by a PI equivalent circuit, and transformer are represented by a series impedance circuit. Generator and loads represent at boundary conditions. Loads are given as such active and reactive power consumption, and generator are usually described by the active power production and terminal voltage. Here we can see the general equation. Actually, if we want to calculate the power flow, we should need to follow some equation. So this is the general equation of power flow. Thus two equations, the one set of equation for each bus network. Here we can see this is how to say the EI and EK. EI and EK the bus voltage magnitude respectively. EI and EK the bus voltage magnitude respectively, and theta I and theta K. Theta I and theta K the phase angle of bus I and K respectively, and GIK and BIK is the this is the Y matrix for power system. This is the I and K terms in the Y matrix in the power system. Yeah, Here we see the AC power flow. That means in the transmission line, we usually we can use the AC and DC. So the power flow have two types. We can consider it in this PPT. We can show the AC power flow and DC power flow. Now let's discuss about the AC power flow. Formulation of AC power flow, building the bus admittance matrix. That means if we want to calculate the power flow, we need to use the matrix theorem to calculate it. Modeling the transmission network and complex impedance as related to the system buses, including line, transformer, and shunt element impedance. General construction rules. If branch exists between nodes I and J, that means if the branch exists between nodes I and J, mutual impedance is the mutual impedance admittance is Yij. The mutual admittance Yij equal to minus y minus small Yij, and self impedance is Yii equal to Yi0 plus summation of I Yij, where J is defined for all branches connected to I. We can see here the one table. It is defined the characteristic based on the typical information. The power flow bus specification. This is the bus type, and here is the active power is P, reactive power is Q, and voltage magnitude is E, and voltage angle is theta. We can discuss about, we can see this, the constant power load. This is the bus type. The constant power load, constant power bus, the load or shunt element, constant impedance, and load and shunt impedance on load tap change voltage constant bus, generator synchronous condenser voltage control bus, and reference generation shark bus. Here you see the schedule that means this one is already given by, and calculated that means we need to calculate. And here we can see some the comment on the CS example. This is the only impedance value are given. That means for this bus the only impedance value are given. For this bus, the secondary side of OLTC transformer. Okay. The nonlinear system solution method, the AC power flow problem is set into the root finding problems, and the common solution technique, the Gauss-Seidel method. This is the one kind. This is the method 1. This is the first AC power flow method development for digital computer. Actually, this is the you can see this is the chart of the Gauss's PF method, the power flow method, Gauss's light power flow method. If let's see here the start and selected the initial voltage, and then we transfer to the do all of the I equal to 1, I 2, 3, 4 is infinity, and I is refer, and then we save the maximum voltage change. Say example, if we cannot, if here is some, we can see here is some loop and logic. Solve the equation E every time EI, that means voltage new, that means every time you can receive the new voltage and refer it, and if everything is okay, then we can save the maximum voltage. The maximum voltage delta E max less than equal eta. If yes, then calculate the follow and print and end. Print the result and end. If here is no, then here we can transfer to the again to do all of the methods. The nonlinear system solution technique, the common solution method is the Newton-Raphson method. This is the Newton-Raphson method. Instead of the treating each bus individually in each iteration, the correction is found for the whole system. The Newton's method is based on the ideal and driving the error of a function to zero by making correction to all the impedance variables such as bus voltage, magnitude, and angle. Setting a point, the equation is f of x equal to k. The peak setting point, x inverse 0, f of x inverse plus eta equal to k. And the use Taylor expansion about f of x inverse 0 plus d. This is the differentiation, and delta x plus eta equal to k. And here you see the Newton method are initial iterative process for the nonlinear system of equation, but it process quadratic conversions to all solution. The set of the first order partial differential equation. The set of the first order, the partial differential equation is called is Jacobian. So thank you. I already covered is 8 pages. Now I need to give the chance to my another friends, Mr. Landry. Are you here, Landry?
Hi, Landry.
Yes, I'm here.
Okay, I can now I can stop to show screen. You can show your screen. Okay.
It's okay. Or I can use your screen, or they can allow me to share mine.
I think you can share. It is better.
Okay. So you
Yeah.
yes. Okay.
Landry, you can share your screen.
Hello, everyone.
Yeah, Vicky,
can
we can
hear
hear
you.
you. Yeah, you could
Yeah,
start.
you can hear.
Yeah.
Okay.
Yeah, we can hear you.
Please continue. Yeah.
Okay. As you have seen above, for solving the problem of power flow, we use Newton's Raphson method. To solve the Newton's Raphson method, we use the two balanced equations, which are power equation, the real power equation, and reactive power. The main purpose of solving this is to find the net power, which are real power and reactive power to be injected at bus I. To find those power, you have to find the summation of the voltage at bus I and the voltage at bus K and the conductance at bus K and the conductance at bus J. The power is equal to the summation from 1 to bus N by making a summation of voltage I and the voltage at bus K times conductance at bus IK cosine of phase angle at bus I minus phase angle at bus K plus suspectance of bus I and K sine of phase angle difference between the bus I and the bus K. Also, we have to find the balance equation of reactive power to be injected at bus I, which is equal to the summation of voltage of bus I and bus K times conductance of bus I K sine of phase angle I and angle phase K minus suspension of bus I and K cosine difference of I and K, where GIK and BIK are the matrix admittance of buses. Here we have a bus I and the bus K. That means it's from bus I to bus K. If we say we have the two buses, we can say it's from bus 1 to bus 2. The injected power of the left-hand side are known for road buses. Here we are going to find the partial difference of two equations, which are real power equation and reactive power equation. We put the partial difference for every element of our equations, which will be equal to the partial difference of real power and the partial difference of reactive power, as you see on here. The partial difference at bus I is equal to the summation from 1 to bus N by making the partial difference of real power by respecting to phase angle K times difference of bus angle K plus summation from 1 up to N, partial difference of real power divided by partial difference of voltage at bus K. This partial difference will help us to form the matrix representation which is for making a conclusion of Newton transfer method. As you see here,